this is our next example for working out. This is our next example for working out the reactions. So as we have done previously, first thing we do is to draw our freed body diagram, replacing the supports with the associated forces so we can do our analysis. Here on the left hand side we have a fixed support, so I'm going to replace that with two forces. On the right hand side I've got a roller support, replace that by one force. I'm going to label the diagram point A to start off with, B at the start of the UDL, point C where the point load is, and then point D at the end of the beam. So the forces, reaction forces, can be labelled VA and HA and VD. Draw in the UDL. That's 20 kilonewtons per metre, and can draw in the point load as well, which is 15 kilonewtons. With this free body diagram, we can then apply our three equations for equilibrium. All the forces in the x direction must add up to give you 0, all the forces in the y direction must add up to give you 0, and the moments about any point must add up to give you 0 as well. Remember the sign convention. Forces going up are positive, down are negative, to the right are positive, to the left are negative, clockwise positive moments, anti-clockwise are negative moments. Applying the first of our equilibrium equations, all the forces in the x direction add up to give you 0. We only have one horizontal force, HA. It's going to the right, therefore it's positive. For equilibrium, it must add up to give you 0. Therefore, your HA value must be 0 for equilibrium. Consider the forces going vertically. This time we have two reactions going upwards. We have a point load, 15 kilonewtons, and a UDL going downwards. VA positive plus VD, which is positive, minus the 15 and minus the UDL, 20 kilonewtons per metre, and the length of the UDL, as you can see from the initial diagram. So the beam is 7.5 metres long. There's a gap of 1 metre at the very start on the left hand side, so the UDL itself is 6.5 metres in length. So there's your 6.5 metres. So the total weight of that UDL will be 20 times 6.5. For equilibrium, they must all add up to give you 0. VA plus VD minus 15 minus 130 equals 0. VA plus VD minus 145 equals 0. Therefore, VA plus VD equals 145, and that would be kilonewtons. If we can work out the value of one of the reactions, then it's easy to work out the value of the other. Applying the last equilibrium equation, moments about any point add up to give you 0. Remember, moments are a force by a distance. We have to show which point we're taking moments about. We take moments about the first support on the left hand side, labelled point A, little bent arrow over the top, the shorthand notation for taking moments about point A. And looking back at our free body diagram, we essentially have HA and VA are at point A, offset distance is 0, so they don't produce a moment. What does produce a moment is the 15 kilonewtons, the UDL, and the reaction VD, because they're all offset from point A. So going back to the moment equation, we have 15 times 3.5 for the point load. When we're considering the UDL, remember what we do is that we concentrate down all of the weight of the UDL into a point load in the middle of the UDL. So we had a space of 1 meter to start off with. The UDL is 6.5 meters in length. So the total weight from the UDL is 20 times 6.5, and that gives you 130 kilonewtons. What we need is the distance from point A over to the center of the UDL. The half distance for the UDL, 6.5 divided by 2 gives you 3.25. Add to that the meter you have at the very start. So the distance from point A to the middle of the UDL is 4.25 meters. Now when we're doing the moments, it'll be the weight of the UDL, 130 times 4.25. The last thing that produces a moment is the last reaction, which is VD, and it is 7.5 meters across from point A. All these moments must add up to give you 0. Now we'll consider which is a clockwise moment, positive, or anti-clockwise moment, negative. Going back to our free body diagram, remember, consider each force as though it were on a piece of string, holding the string at the point that you're taking moments about, in this case point A. So for the 15 kilonewtons, if that were allowed to freely rotate around point A on a piece of string, it would want to rotate around in a clockwise manner, positive moment. Likewise, for the UDL, we consider the load concentrated in its middle, where the 130 kilonewtons is. Again, on a piece of string, allowed to freely rotate around point A. How would the 130 kilonewtons want to rotate around? It would want to rotate around in a clockwise manner, positive moment. Considering VD, again, if it were allowed to freely rotate on a piece of string, you're holding the string at point A, it would want to rotate around in an anti-clockwise manner, therefore a negative moment. Updating these into our equation and then working this through, 15 times 3.5 gives you 52.5. 130 times 4.25 gives you 552.5 minus 7.5 times VD equals 0. Bring the two numbers together, 6.5 minus 7.5 VD equals 0. Move the 7.5 to the lower side of the equal sign, making it positive. Then divide through by the 7.5. That gives you your first reaction, VD, which is 80.67 kilonewtons. With the equation just at the top of the page, VA plus VD equals 145. We can substitute in our known value into that equation and work out the value for VA. Substitute in our value. bring the 80.67 to the other side, calculate the difference, 64.33 kilonewtons. So our answers in this case, HA is a value of 0, VA is equal to 64.33 kilonewtons, VD 80.67 kilonewtons.